All right, good morning. Let's do this. Lecture on inheritance, and we're setting up programming task 4. In 4, I mentioned this last time, but there's a pretty good difficulty spike from task 1 to 2 to task 3. There's also a pretty good spike from task 3 to task 4. This is where the course really starts heating up. So if you've gotten complacent with tasks 1 and 2, actually I wanted to pull stats for y'all on task 3. I have it open right here, just got to refresh. Task 3 expected deadline. A lot of y'all were working late last night. I checked last night, and it was looking a lot more abysmal than this. 35 completed task 2 or task 3 before the expected deadline. That ain't as bad as it was looking last night. And 1, 2, 3, 4, 5, 6, 7. 7 students submitted without getting credit before the deadline. So only 7 who were attempting the assignment and didn't finish it. Those aren't bad stats. The bad stat is the number of students who didn't even bother submitting. 42 out of 59 was that 17 students didn't even make a submission. Is ridiculous. I do not know what to do with students like that. I don't even know if there's anything I can do if they're just not even gonna submit anything. Like what do I do? So it's not too bad. 7 students attempted the deadline and didn't make it in time. But those are the stats. What was it? 35 out of 59 met the deadline. Task 4, make sure you're keeping at it. And then there's a decent break after this, by the way. I mean, well, we got the usual 4-day weekend, 3-day weekend, sorry. And then trees. And then we have a day off and the midterm coming up. So it's a while before there's another task. I mean, there's task 5, but then a while before task 6 comes. So there's a little bit of a breather. Of course, you got to study for the midterm. Studying for the midterm, in my opinion, would be easier than completing a task. But and then we're almost done already. This is, it goes fast. I don't think there's anything specific I want to talk about with task 4 either. It's I thought there was one method I wanted to point out like I did with task 3, but nah, let's just jump into it. Okay, inheritance. Okay, so we're going to simulate making a game. No, we're not actually going to make this whole game. In the fall and spring semesters, last semester we started to actually have a full game as the project, as the combination of all the tasks. I didn't run in the summer for a few reasons, partly because it's fairly intense, and condensing that down to 6 weeks, I don't know, it'd be rough, it'd be tough. So we're not going to build any full game. But we do want to simulate some functionality of a game. So that's what we're going to do today. And that's how we're going to show inheritance, is through this example. We're going to create a game that has health potions and weapons, these 2 objects that a player can interact with. And that's really all the mechanics we want to build. That's all we need to be able to motivate inheritance and talk about everything we need to do with inheritance. So let's take a look at what that looks like. So let's build a health potion class. Looks like I'm covering up a little bit of the text here. It says print line behind me. Print line 4. And let's take a look at how to build these classes. So I have a health potion class here. I want to know a few things about it. I want to know its location in the game, and I'm thinking this as a top-down perspective 2D grid style game. So I want to know the health potion's X and Y location on that grid, and I want to know the amount that it's going to heal the player, or the amount that it'll increase their HP when this health potion is consumed. So I have a constructor. The constructor is going to initialize all 3 of the instance variables in this case. That's not always the case. That is the case right here. and that's all the constructor does is initialize those three variables. And then a use method, what happens when a player uses this, and at least for now, we're going to simulate using these objects. Right now, use is just going to print to the screen and pretend that the player was healed this increased amount of HP. Okay, so cool, but all that should be review. Every one of you should be like, yeah, we just did that on test 4 3 times with 3 different classes, test 2 actually, on 3 different classes. What are we learning today? And of course, the topic of today, the title of the lecture gives it away, it's inheritance. But what is that? What does it look like? And why does it help us? That's what we want to talk about. So let's modify this example to take advantage of inheritance, our new topic for the day. So with inheritance, what I'm going to do is actually create a second class, this game item class, and move some of the functionality of the health potion class into this second class. So game item is going to have, and it depends on every application. For this application, I'm going to say game item is going to take the location information for a health potion. So game item is going to get that X location, Y location instance variables, and a constructor that initializes X location and Y location. So that's my game item class. It's going to have anytime I need to do anything to do with location, game item class is going to be responsible for that. And then we get to our inheritance proper. So in the health potion class, we're going to inherit all of the state and behavior from the game item class. And I'm going to do that using the keyword extends. So I'm going to say health potion extends game item. And once we write health potion extends game item, we're using inheritance at that point, and health potion inherits all the state and behavior of the game item class. That means the state, all of the instance variables, and behavior, all of the methods. So the health potion class inherits all of the instance variables of the game item class, which is X location and Y location in this case. This extending game item is it's a little bit different, but it's almost like taking all of the code in the game item class and pasting it into the health potion class. So these two instance variables, X location, Y location, health potion inherits them from game item. So every object of type health potion is going to have 3 instance variables, increase X location, Y location, just like it did before we modified our example to use inheritance. So we inherit all of the instance variables from the class that we're extending or the class that we're inheriting from. We also inherit all the methods. Right now it's only a constructor. We'll add more methods here as we go. But we also inherit all of the behavior or methods from that class. So when we extend a class like this, we gain access to all of its methods, and we can call those methods from our class that's inheriting from the other class. And we got to get some vocab out there, because it's those first 2 slides is weird the class that inherits from the other class. Let's get some vocab so I can name these by name and not struggle with what to call them. Is when we have a class that extends another class or a class that inherits from another class, we say that the class that we're inheriting from is the superclass, and the class that's doing the inheriting is the subclass of the other class. So health potion is a subclass of game item, and game item is the superclass of health potion. And there's also a second analogy. The family tree analogy works here too, is health potion is the child class of game item, and game item is health potion's parent class. So 2 different analogies, and for some reason it's just stuck in my brain where I usually say superclass and child class, so I actually tend to mix these up. But if you hear them on purpose, not mix them up. Um, but if you hear either of these, parent class, child class, superclass, subclass, both of them are perfectly valid. Those are all valid ways to talk about inheritance and the relationship between two classes in inheritance structure. Yeah, I gotta be done with this tea. I like drinking while I'm streaming. And one of the most important things about inheritance as it pertains to your memory diagrams, and something I'm going to say so many times, you're going to be like, why is he still saying this? Like, we get it, man. We get it. Is that the superclass constructor has to be called from the child class. And I'll say this so many times, and you will think that eventually you'll be like, he already said about the superclasses so many goddamn times. Why won't he shut up about it? There will still be students who make this mistake on the traces. No matter how many times I say it, I suspect there's students who don't watch lecture, because how the hell could you watch my lecture and miss the super constructor call? But the super constructor call has to be called. When you're in a child class, the superclass constructor is always, 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 100% of the time, it is always called. So that's how we construct our objects when there is inheritance. This constructor, this game item constructor, is called using this keyword super, or use the keyword super and then pass the arguments matching the parameters of the superclass's constructor, and then call that superclass constructor. The superclass constructor always has to be called. And notice I'm going to be careful with the way I say that. You don't always have to call the superclass constructor, but the superclass constructor is always called. So if any of you have taken Java before and you've had learned Java, there is a distinction there, but it is always, always, always called. And I'll talk about that distinction in a few slides, but just want to get ahead of that before someone's like, well, excuse me, I didn't always do this superclass constructor call. So this has to happen. If this line, in this example, if this line isn't here, we get errors, our code doesn't run, everything blows up, everything's bad. The superclass constructor is always, always, always called. If the superclass constructor takes any parameters at all, that call must be explicit. So since we have any parameters at all in the superclass constructor, we have to call it, and it has to be the first line of our constructor. The very first thing we do has to be a call to the superclass constructor using this syntax: super, the keyword super, and then the argument list. There is a case where if the constructor has no parameters, this call doesn't have to be explicit. We don't have to call super with no arguments, super, open paren, close paren, semicolon. We don't have to put that here, but the superclass constructor is still called. This is one case where Java has our back and says, you know what, you don't have to tell me that you're going to call the superclass constructor with no arguments to match its no parameters. You don't have to tell me that, because I know that you have to do it, and since there's no parameters, there's no choices to make, and since it has to be the first line of your constructor, there's no decisions to make at all. So Java will just call the super constructor for us in this case. So you don't always have to explicitly call the super constructor, but the super constructor is always, always, always called, and it's the first thing that happens when your constructor is called. So that's your intro. I'll say this a whole bunch more times, but that's your intro to the superclass constructor is always called. That is, when it comes to our memory diagrams, this is one of two things that you need to know with inheritance. And in fact, these are actually the last two things we have to talk about with memory diagrams. I'll still give an example in trees, and I'll show how traces work with trees. But there's no new concept to talk about. Arguably multiple recursive calls, and that's why I still do a memory diagram with it. But these are the last actual new concepts to learn for memory diagrams. And then after today, you theoretically could do the final, the final two. But the midterm exam, the final exam, all the quizzes and everything, you would be able to do every one of them. So that's one, and we'll put a pin in the other one. There is a second one but we got a lot of more groundwork to cover, a lot more foundation before we can talk about the other one. It's going to be what method is called when a method is called. That's going to be a big topic today. Today and with polymorphism. I gotta just finish this. I like taking sip breaks. Okay, but why are we doing this? I alluded to that we would talk about why we even use inheritance. So let's talk about that, because this example is kind of dumb. Like, why would I ever do this? Because this is a lot more complicated than the first initial version of this code that we saw. So this code does the same exact thing. Little asterisk, but things that we don't have to worry about in 116. It's technically a little bit different. But this code does the same thing that we saw in the previous example, except now instead of one class, we have two classes, which in Java that means we have two files. So our code is more spread apart in our code. And we have to understand how inheritance works. So this code is a little less legible because when we're looking at the health potion class to figure out what it does, we, one, have to know what inheritance is, and two, have to go over to the game item class and click between the two files a bunch of times to figure out what a health potion even does. So we sacrifice a lot. It's harder to write, it's harder to read, but it does the same exact thing. So why would we ever do this? Why? This is a pain. Why do we learn inheritance at all? This just sounds like more work for no gain. And in this example, it absolutely is. And the answer to why is when we have multiple classes that are extending the same superclass. So when we have two child classes, weapon and health potion, this is where we start to see the benefits of inheritance. So when we have a weapon class and a health potion class, we want these both to behave like game items in our game. So our game has game items that can be of different types. In our case right now, weapon or health potion. They're both items in our game, and they're both going to extend the game item class to get all of the state and behavior that every game item should have. And then inside the weapon and health potion classes, the only thing we should be adding is, one, the superclass constructor call to make sure the game item stuff that we inherited works the way we expect it to. But two, and more importantly, well, they're both important. But two is anything that's specific to that type. So the weapon class is going to have everything that a weapon needs to know, which is the damage output in our case. And a health potion knows everything about how to heal the player when this potion is drank. Everything else, everything that's not specific to these types, goes into the game item class. So both of these types and any game item in our game needs to have some location in the game. So we're going to put all the location information in the game item class and let the other classes inherit from game item. And even that, you might think this is still more work. Like I could just put X location, Y location in each one of these, and then instead of a superclass constructor call, just assign the instance variables directly. It's not that much gain, right? Well, it becomes much more gain when we have more complex of an example. So I only can cover a small lecture example. It has to fit in one of these lectures, and I got a lot of stuff to talk about. So I can't show too complex of an example, but once the code does get more complex, you really start to feel the benefits of inheritance. So for example, we don't just want a game item to have a location, we want the game item to be able to move too. So we add a move method that's going to take your dx and dy and then move the object by that amount in that direction. Once we add this method to the game item class, we add it here once, and then both weapon and health potion inherit that method from the game item class. So now from any object of type weapon or any object of type health potion, we can call the move method. So we only had to write a method once, but we have that method available to us in two different classes. That's where we really start to benefit from inheritance. And this is just a simple move method. You might still say, well, I'll just cut and paste that and put it in both of my methods. But what happens when game item gets to be 200 lines of code and 10 methods, and you're doing all kinds of physics stuff, you're detecting collisions and doing a lot of complex math and big methods, you don't want to take 200 lines of code and cut and paste it into every single one of your methods. I mean, maybe you do. Who am I to tell you what you want to do? But you shouldn't if your goal is to write good, clean, bug-free code. Because one of the issues, well, one, you can write it once and then cut and paste it twice, which is, I don't know, it's bad. But it's bad on its face. But the real issue with that, the real problem that you're going to eventually get into, is when you have to, when one, you have a bug in that code, or two, you just want to update it, you want to add some more functionality. Now what you have is a situation where you're maintaining the same code in two different locations. So you update your code, you add a way for objects to bounce off the ground when they land on the ground, something like that. You add it to the weapon class, and then you have to remember to cut and paste that into the health potion class, and you have to make sure to cut and paste it exactly correctly. Sometimes you're just gonna straight up forget to do that, and then you have weapons and health potions behaving differently. There's a lot that can go wrong when you're maintaining two pieces of identical code. But when you put it in the game item class, you put it there one time, you test it one time, and you're done. That's it. If you put it in there twice, and you're actually testing like you should be doing, you have to duplicate your test cases as well. You have to test weapon and health potion separately. If it's in game item, you just test it once, and you're done. And of course, the big issue where this problem gets multiplied by, well, hundreds, literally, is with two, it's not too bad. Two classes, whatever. But what happens when I'm adding more and more game item types to my game? What happens when I have hundreds of game item types? I'm thinking of new ideas. I'm like, oh yeah, that'd be cool to have rocket launchers in my game. I'm going to add rocket launchers. Every time you add a new game item, you extend game item, and you get all of the code in the game item class. If that's 200 lines of code, if it's 1,000 lines of code, doesn't matter. You're just grabbing all of the game item code so that your new items will behave as game items do. And then you're just worried about, what does my new item type do? How does it behave? What does it do when the player uses it? Are there any instance variables that it needs to be able to do something different based on, what specific object it is? That's where we really see the power, is when we have lots and lots of classes extending the same base class. So that's why inheritance. It makes our code way easier to write and maintain when we have multiple classes that have a lot of common functionality but are still different enough that we need different classes. We're going to factor out all of the common functionality and put it into a superclass, and then have them all extend that superclass to share that state and behavior. So that's why inheritance. And that's how I'll motivate it here. In my opinion, the biggest advantage of inheritance is polymorphism. But of course, we'll save that for the polymorphism lecture. Polymorphism really enables us to do things that we would never be able to do otherwise, and we can't set up polymorphism without inheritance. So that's the bigger selling point, is polymorphism, but we're not talking about that today, so I'll just tease it, foreshadow it a little bit. All right, let's do this as a memory diagram. Cue this up, and let's grab this code. Make sure I grab the right one. 3905. Well, why is IntelliJ closed? I didn't close IntelliJ. I blame Windows. Oh, why do I feel lost? That's the wrong week. It is week 5, right? Why does it seem like the code's missing? List. Or are we on week 7? Oh my goodness, we're on week 7, that's why. Man, summer, it even catches me off guard how fast the summer goes. Goodness gracious. Week 7 already. Which means it's lecture 7. Is that even true? This isn't lecture 7, this is lecture 6. Oh, I know why, because there's a whole week, this whole week 6. This is a testing week where it's like testing tips and tricks. I forgot I have to cut that for the summer. There's just no time for it. We don't introduce any new concepts that week, but there are like things that can make your testing easier. I feel like not every student, but every struggling student, I feel like ignores all my advice in that week anyway. So it is what it is. It's just one loss we take in the summer. All right. That's what was tripping me up. Man, that had me going for a bit. All right, so let's trace this code and let's use the code that we just saw. So let's do our first trace using inheritance. All right, every Java program starts with the main method. Main. We have weapon. This, so I don't forget. If it's a non-static method, if the method doesn't say static, we're calling this constructor, it is not static. I'm going to put this immediately before I forget. I'm never forgetting that. I'm just going to put it on right away. Okay, so we're using inheritance, and we very quickly get to the part of what we're doing that uses inheritance. So this looks like a regular constructor call, and for the most part it is. But we do have inheritance going on as well. So let's talk about the differences here. There's not too much. There's not too much to add to memory diagrams, but we do have to pay attention to everything that is added. Let me get some more spacing here. I have it crunched down because on the slides I can fit way less code. When I'm streaming like this, I have a lot more screen real estate to work with. It's nice. Is when we create an object of any type, we look at all the instance variables and we put those instance variables in the object that we're creating. So damage is a variable of this object, this weapon object that we're creating. We go to the weapon class, we grab all of its instance variables. That we've done, I mean, admittedly not too many times, but enough times. We've seen a lot of examples of that. When it's inheritance, though, when you see this extends game item or extends anything, you see the keyword extends in a class, you have to continue this process and go to the superclass and grab all of its instance variables. So weapon inherits all of the state and behavior from the game item class. So we're going to go to the game item class and grab all of its state, which is all of its instance variables. So we grab X location and Y location from the superclass. So we get all of the instance variables of the class matching the type we're creating, and also from its superclass, we go to the superclass and get all of those instance variables. So an object of type weapon will have all of the instance variables of the weapon class and the game item class. And I usually get this question, so I'll get ahead of it here, is the order of these instance variables does not matter. In your traces, the computer will put these, Java will put these in a specific order, and to be honest, I don't even know what the order is. I think it's the superclass first, but in your traces, the order doesn't matter. Hell, you could do Y location, damage, X location, I don't care. It's like a hash map. The order really is irrelevant to us. It's not going to change the behavior of your program. So I don't care what order these go in. All right, so we get all of the state of the object, and then we're ready to call the method. We got all of our instance variables in the object, and then we're ready to call the constructor. We have 3 parameters: X location, Y location, damage. They happen to match the actual instance variables, all the instance variables. That does not have to be the case, but I'm going to look at my constructor parameters to figure out what to put in this stack frame just like every single method call you've ever done in your lives. I keep stressing this, but I know a lot of you will still make this mistake on the quizzes. I don't know. I say it so many times every semester, and I'll still see that mistake. But the parameters go in the stack frame just like they've been doing since 115. That part doesn't change just because it's a constructor. X location, Y location damage is 3.9. The order of these ones does matter because I have to match them with the arguments. And 10. So I'm getting these arguments matched to these parameters, just like any method call you've done since 115. And then we have our next inheritance specific thing, the superclass constructor. Your superclass constructor is always, 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 always called. Always. In this case, it's explicit. And actually on the quizzes, I'm going to make it explicit, just so it's not a gotcha question. But the superclass constructor is always called. So what that means in our trace is something kind of special that we haven't seen before, is we're going to have, this is a method call, so we have to have a stack frame, is what we're going to have is a second constructor call. So we're going to have two constructor calls that are going to create one single object. So this is a constructor call to super, and whenever you see super, you can kind of replace that with the superclass name. This extends game item, so this is game item, which means we're calling this constructor right here. So we're calling the game item constructor. When you have a super constructor call, this, it's a non-static method. It's going to have the keyword this. This is still a reference to the object that's being created. So it gets this from the other constructor, the weapon constructor in this case. There's no new instance variables to create. I guess when you do your traces, at this point, you could add X location, Y location to your object. It's fine. I would never know, honestly, when you submit a trace, because your trace will be the same. And we have the parameters, X location, Y location. Which get X location, Y location from the other stack frame, which is 3.9, negative 0.5. And then we execute the superclass constructor. This dot X location, this dot X location equals just gotta make sure everything's working right. Equals X location, and that's on the other side of the assignment operator. That means this is a separate expression. It starts over at the stack frame again. So from the game item stack frame, X location 3.9. So 3.9. This dot Y location equals Y location, negative 0.5. And that's the end of our superclass constructor call. So this returns and gives control back to the main constructor here. So this constructor just resolved, doesn't return anything, it doesn't do anything special. It's a kind of like a regular method call. Basically a method call that returns void is kind of how you could think of it. Doesn't do anything special that constructors usually do. It's just a call to finish initializing or begin initializing the object we're creating. And now that that returned, we go on to the next line. This dot damage equals damage 10. And this constructor returns, I forgot my return arrow, and returns OX100 to the weapon object, or to the weapon variable. So what we have here is that this resolved to a reference to the object that was created, OX100, that's old news. We've done that plenty of times. But in the process of calling this constructor, we actually had two constructors on the stack. And this always, the superclass constructor, when you have inheritance, The superclass constructor is always called, meaning if you see the keyword extends in a class that you're creating an object of, that means you will have two constructor calls here, or more. I mean, game item might also extend something. That you'll have two constructor calls here. You must trace the superclass constructor call. Like I said, I'll always make it explicit on the quizzes just because I think it's too much of a trap question. But even if I didn't put super here and there was a constructor, superclass constructor that didn't take any parameters, you do have to know that that superclass constructor is still being called and it still has to be traced. You'd have to trace two constructor calls. So if you see extends, you better have two constructor calls at least. Do not forget your superclass constructor calls. That is one of the instant automatic fails on the OOP quiz. If you miss a superclass constructor call, it's easy to grade. I mean, if it's missing, it's an easy 0.0. You didn't get that quiz. Don't forget your superclass constructor calls. It's hard to miss them when they're explicit like this, but some students will still miss these calls. And when you miss an explicit superclass constructor call, it's clear evidence to me that you need some more time studying inheritance to understand what's going on there, to understand what this call is doing. So we have two constructors. We call two constructors to create a single object. And the trick to remembering this, if you're struggling to see what's going on there, the trick to remembering this is the same exact trick as we've done before with object creation. If you see the keyword new, a new object's being created. If you don't see the keyword new, a new object is not being created. So when we call the superclass constructor, we're not saying new super. We're not doing that. We're just saying super. We're just saying call the superclass constructor, but do not create a new object when you do so. So we're calling the superclass constructor without creating a new object, and we didn't use the keyword new. So the same thing applies that we talked about before. Whenever you hit the keyword new, you know you're clicking this button and creating a new object on the heap. If you don't see the keyword new, you are not clicking this button and not creating a new object on the heap. So we have a constructor call that does not create a new object, but we also didn't use the keyword new, so it should be fairly easy to remember. If I hit the keyword new object. If I don't, I don't. So two constructor calls, one object. Okay, so that's superclass constructor calls. Critically important. That is the first important thing that we need to know for our traces with inheritance, at least. And honestly, for the assignments, for the programming tests, the inheritance part of it isn't too crazy because the way I have to write the assignments in a way that they can be auto-graded in AutoLab, I pretty much have to give you the inheritance. I say write a rateable class and have song and movie extend rateable. I basically have to hand feed you it. So it becomes like a regular assignment. You could do test 4 before this lecture, probably even. So really what I got to prep you for is the quiz in this lecture and showing you what inheritance is. Like, it's better to do test 4 if you actually understand what's going on. So the lecture is still important there too, even if you're not asked to use inheritance on your own. So anyway, weapon.use. Weapon.use, from this object, there's only one object, but from that object we're calling the use method. And this is our other really important thing for inheritance, which is going to be pretty trivial in this specific example. Did I write OX100 there? This. Which is going to be pretty trivial in this example because, again, there's only one object, there's only one use method. There's no question what's happening here. But when there is a question, like in the next example we do, it will be in question, is which method is called when a method is called. This is the second memory diagram thing that we need to know to be able to read code that uses inheritance. Weapon.use, which method is called? Because I have two classes here. Where do I look for this method? And I've been setting this up all semester. The way we call methods is we're going to look at, we have weapon.use, so this is OX100. It's called from an object of type weapon. So we take the weapon class, this object of type weapon, we look in the weapon class for a method called use. This is what we did in the party and character example. We had 2 win battle methods in different classes. This is how we figured out which one was going to be called. And it's going to be the same thing with inheritance. That's why I explained it that way before. So it's nothing new. We don't have to relearn how to find the method when we do inheritance. So it's this method right here, this use method, which is going to print damage dealt, this dot damage, lowercase d, dealt, colon, space, this dot damage, which is 10. Java auto converts that into a string for me with a concatenation operator, and this method call ends. Okay, moving on, weapon.move. We're going to create a move stack frame. Weapon dot, it was OX100 of type weapon that called this method, so this is OX100. And that object is of type weapon, so we're going to look in the weapon class for a method named move, and now things get a little bit different. We got to panic a little bit here, because we look in the weapon class, we do not find a method named move that takes 2 doubles. We don't find one. It's not here. What do we do? Is our code bugged? Does our program crash? Does it not compile? What's going on here? So we don't find it in the weapon class. And this brings up our last big point in inheritance, for memory diagrams at least, is when you don't find the method in the class matching the object type that you're creating or that you're calling it from, when you don't find it, you go through your progressions and look for that method in the superclass. You only do this if you don't find the method in the class matching the object type. You start in the class matching the object type. If you find the method, like we did with use, you find the method and you just stop right there. You don't ever look at the superclass because you found the method in the child class. In the case of move, we did not find it, so we're going to continue our search in the superclass. We're going to go to the game item class. We're going to look for a method named move that takes 2 doubles. We find it right here, and this is the method that's going to be called. And that fundamental concept, we're going to see that a lot today and in polymorphism, is which method is called when a method is called. That in your superclass constructors, that's, you just have to not even remember to do it. You just have to know what happens when you hit this line. With which method is called, when a method is called, this one's a little trickier. There's some more steps to go through, and you got to go through the progression. Start in the class matching the object type, look for the method. If you don't find it, and only if you don't find it, you go to the superclass and find it here. So it's this method. We have 2 parameters. Move my mic a little. dx, dy, which get the values negative 0.5 and 1.3. And then we run the code. This dot x location plus equals dx. So subtract 5 from this, should be 3.4. And this dot y location, negative 0.5 plus 1.3. I gotta make the math a little hard on myself during lecture. Not that that's hard math, but in the middle of the lecture I got 8,000 other things on my mind. I tend to make small math mistakes fairly often. All right, so we got our move method called, and then that's the end of the program. So superclass constructor calls and which method is called when a method is called. Those are the 2 big things we have to know. And here's our final state of our memory diagram after all that. Okay. Opera updated on me. I think that's part of what went wrong. I think this computer, this restarted. It was Windows' fault that IntelliJ was closed. Yeah, this machine restarted without my permission. I hate Windows. All right. Moving on. No, we have a few more slides to cover. We got to talk about the object class. So the object class whether if your class does not explicitly extend any superclass, it implicitly extends the object class. So if we don't write any extends here, we actually are still using inheritance. Every class we've written, every class you ever write in Java does extend a class. It extends a superclass. If you explicitly extend a class, you know it obviously extends something. So when in health potion we extend game item, we know health potion extends game item. End of story. Like that's what it extends. But if you don't type anything, it implicitly extends object. So these two classes are identical. This class, this game item extends object, or we can explicitly type extends object. We usually don't explicitly type it, but game item does extend the object class, which means every single class in Java extends object, either directly or indirectly. So our, which brings up inheritance chains. I guess I didn't explain that yet. I alluded to it, but I gotta actually explain it. Is since game item extends object and health potion and weapon extend game item, health potion is going to get all of the state and behavior of game item because it extended it. But since game item extends object, game item gets all the state and behavior of the object class, and then so do health potion and weapon. They get all of the state and behavior of both game item and object through the inheritance chain. And we can have as many classes as we want in the inheritance chain. We can have a class that extends a class, that extends another class, that extends another class, that extends extends object. And that last class, that first class that I said in the chain, is going to have the state and behavior of every single one of those classes. So, and that means, so everything extends extends object either directly or indirectly. So what's in here? Well, those two methods we talked about last time, toString and equals, how we got away with using these methods in a linked list when we didn't even know the type of the type parameter. How were we able to call these methods? Well, it's because they live in the object class, and everything in Java, every object in Java inherits from the object class. So every single object in Java has a toString method and an equals method, and a few other methods that aren't relevant to us in 116. So everything has these because they live in the object class. So that's why we got away with dot equals in that find method, because it's in the object class. Okay, let's keep going. So override. So we say that we extend the state and behavior. When we extend a class, we inherit all the state and behavior of the base class. And that means health potion is going to get, some of these first slides are review because usually there's 2 full days in between here. I think I can go through it quick. We just saw this. But health potion is going to inherit the use method, so it gets that method. But what if we don't want 100% of the state and behavior, 100% of the behavior of the class we're inheriting from? What if we don't want this use method that just prints item used to the screen? I want my health potion and weapon classes to do something specific to them. I don't want them to just print, hey, I was used, that I inherited from the game item class. Well, then we're going to use an override. So we're going to override the method, create a method with the same signature, and now this is the method that's going to be called when we call use from an object of type weapon. We're going to get this printed to the screen, and we won't get this method at all anymore because we overrode that definition with a new definition that's specific to the weapon class. and that's overrides. We're replacing some of the inherited behavior with behavior specific to that class. And let's talk about the override annotation. I should cut this down a little, but I still want to talk about it just because it comes up a bit. I want to squash all the questions and get you understanding this override. So there is an override annotation, and this override annotation is going to tell Java, it's going to tell the compiler, hey, I'm about to override a method. So this annotation is saying the method I'm about to write overrides a method that I'm inheriting. I want to replace the behavior that I inherited with this behavior. That's what the annotation is telling the compiler and telling Java. It is optional. The override annotation has no effect on the behavior of your code. As long as you have the same signature, the same method signature as the method that you're overriding, it will be overridden with or without the annotation. The annotation has no actual effect on the execution of your code, meaning like in a memory diagram, in a memory trace, you can just ignore the annotations completely. They have no effect on the execution of your code at all. There's no difference between this code and the code with the annotation. The reason to use the annotation, and why I recommend it and why I always use it, one, it makes your code more legible. Somebody looking at this code knows absolutely that I am overriding a method. Like, there's no question because I have the annotation. It's there. But on a more practical sense, well, actually that is practical, but also the override annotation, since you're giving the compiler a heads up that you're about to override a method, if you make any mistakes, if you have a typo like this capital S right here, the compiler is going to flag you down and say, hey, excuse me, you told me you were overriding a method, but this method signature does not match any of the signatures of the superclass that you're inheriting from. You don't have any method with that signature, so what are you overriding? Like, maybe you should go take a look at this and either delete the annotation or fix your method depending on what your goal is. So the override annotation is giving the compiler more information to be able to help us write more effective bug-free code. So the override annotation is very helpful in this sense. If you have a typo, the override annotation, you're going to find that right away. If you don't have the override annotation here and you have this typo, you just get buggy code. You get buggy code, your code doesn't do what it's supposed to do. You call the use method, it's not going to call this method, it's going to call the inherited one, and you're going to be wondering why your weapons are buggy in your game. With the override annotation, you're never going to make a mistake like that. You'll make a mistake, but you'll catch it immediately because the compiler is going to tell you that you made a mistake. And that's nice. The fewer, because we will make mistakes. We're human. We make mistakes. The fewer opportunities you give yourself to have those mistakes actually break your code, the better. And the override annotation is going to help you. But it is technically optional. I say that because the other 116 instructor, Paul, he doesn't use the override annotations. I think for a while he didn't even know it existed. So I say that just to show the two differences. It is optional as long as you always have your method signatures correct. You don't need the annotation. But I like it because I make mistakes, and I want those mistakes to be caught by the compiler. Okay, we gotta come back for toString. And we're doing one, oh, where do I want to go? I want to park this on toString. What am I doing? All right, and let's grab the second tracing code, which should have everything we need for both those traces we just saw. Trash can, all that, all my hard work just gone. Hide toolbar, full screen, paste this. This is by far our biggest trace. And it's our first one. I can't fit fully on the screen. And we have some I/O. Oh man. I'm gonna hide the print lines. Oh. Yeah, let me hide the print lines, I guess. Since we're not talking about those yet. We're not talking about all the two-string stuff yet. Yeah, and the use methods print to the screen. All right, well, we'll fit everything on here one way or another. Even if I do have to just scroll up and down, it's not ideal. But all right, so weapon equals new weapon. Main stack frame, everything starts there. Weapon, this is similar to what we just saw, creating a weapon object. We have a weapon constructor. We're going to create our weapon object, map it to the constructor. We got CSE116. We're creating a new weapon, so let's go to the weapon class. We have a damage instance variable. And then we need to go to the superclass to find any extra instance variables, and we have X location, Y location. Then we're ready to call the constructor. We have X location, Y location, damage as the constructor parameters, so those all go in the stack frame, and only the constructor parameters go in the stack frame. Oh, that's a typo, but I'm just going to turn my brain off and do what the code tells me. That's a lowercase l, so I'm going to put it as a lowercase l. By no means would that ever fail your quizzes, but I'm going to read the code and do exactly what the code tells me for a lecture example. And then those get assigned the arguments, 1.3, 0.7, and 100. 100 damage we're dealing with this weapon. Then the superclass constructor, when it's explicit, it's hard to forget, but the superclass constructor is always called, whether it's explicit or not. And it can only be implicit if the superclass constructor takes no parameters. So the superclass constructor, superclass is game item, so I'm going to the game item class and calling its constructor without creating a new object. I'm just calling the constructor. This is still a reference to the object that's being created. We have two parameters, X location, Y location, both with capital L's this time. X location we're creating a weapon, so X location with the lowercase l here. X location 1.3 and Y location 0.7. We run this constructor, this dot X location equals X location 1.3. This dot Y location equals Y location 0.7. This returns. We go back to the weapon constructor, this dot damage. This dot damage equals damage 100. This returns and gives OX100 up here. So don't forget your superclass constructor calls. That's one of the big things with inheritance. Let's run it back. Let's do it again with health potion. We're going to get potion. Health potion. I only got to type that one more time. I'm not going to copy it in my clipboard. This returns the potion where you see the keyword new, so I'm creating a new object. Map the constructor to get my color coding. We're creating a health potion, so let's look for all the instance variables. I see one, it's increase. I also see that we're extending game item, so let's go to game item. I see two instance variables, X location, Y location. And then we rolled OX200 here. And then we go to the health potion constructor, which calls its superclass constructor. Its superclass is game item, so we go to game item and call this constructor. So game, oh, whoa. Do I have audio now? Okay. Do I have audio now? We have audio now. Goodness, how long was that gone? We run this constructor, this dot, this full street. That's all. No, we're current. We rolled this. So the super game. And some happened right here during the health potion super constructor call. Okay. Okay. Well, we'll have to live with that. If anyone complains, I'll tell them they should watch lecture live and let me know. Thank you for letting me know, first of all. Thank you, Lime. Well, because it would suck to lose all the rest of the lecture. But yeah, people that watch lecture live, sorry you missed some audio. Somebody's got to be here to tell me when that shit happens. So thank you, Lime, for saving the rest of the lecture. Okay. So we can use the keyword super to access the superclass, the superclass's method that we overridden. So a few bits of, well, of course nobody heard me say the lead up to that. But which method is called? Let me do a little bit of, yeah, because we missed all the which method is called stuff. Which method is called when we call a method? That's the frustration, because I can see like 2 people are here to actually watch lecture live. Why do we even do live lectures if no one's going to show up? I should just point you to the recordings from last semester. But that frustration aside, let's I'll recap a little bit of this. So the toString method is being overridden here with weapon. I'm purposely not using the annotation here. So we're getting, when we call toString from weapon, we get this method, and then that's the end of our progression. We don't search anymore. When we call it from health potion, we get this method, and we don't search anymore. And with health potion, what we often want to do with overrides is extend the behavior of a method we're inheriting, not completely replace its behavior. So we're going to get super.toString. The super keyword is going to go to the super class and call a method. So we're calling game items toString right here, and getting that method call here, and then adding some health potion specific behavior here. So we're not completely throwing away the method that we inherited. We're calling it and then adding more functionality to it, which is very common. We're extending for a reason, and usually it's because we want that state in behavior. But if we want more, then this is how we can do it. We can use super to call that method that we're overriding. And now I'm wondering how that happened. So on OBS, my mic got muted. There shouldn't, like that shouldn't happen. I was not messing with OBS at all. Regardless, let's trace these toString methods, which conveniently cover the same concept that we were talking about before, but with a little bit more. So we'll still get those concepts that were covered while the mic was out. Let's see if I can get these. There we go. It's a balancing act getting everything on the screen. Okay, so we have printline weapon. Remember, printline is going to implicitly. Now I gotta look over there every time. And the audio is maxed. I gotta adjust my audio levels too. Now I gotta look over there every. Maxed. I gotta adjust my audio levels too. I think that's fine. Beamer Realm? What's up, Beamer Realm? If the audio's too low now, I decrease the gain a little bit. If it's too low, let me know, but it looks like I was in the red and peaking a bit there. Okay. All right, so printline will call toString. I won't do this on a quiz. I'll make it explicit just so it's one less simple mistake you can make of forgetting to call toString. But this will implicitly call toString. The printline method does call toString. So I'm calling weapon.toString in this call. So weapon.toString. This method, this object is calling toString. And we have this CSE116. And we're calling the toString method. So we're looking in the class weapon for a toString method. We go to weapon, we find a toString method right here, and this is the method that's being called. So this method right here, we get a local variable out, which gets the value weapon damage this dot damage 100. Copy that. And then that's returned. Now notice that we did not even look at the game item toString method. Even though weapon inherits this toString method from game item, and game item inherits a toString method from object, it doesn't matter because our progression said from the weapon class, we found toString right here. That's the one that's called. End of progressions, end of story. So that's what's printed to the screen. So we have an IO line, weapon damage 100. I think I can get away with just leaving the last output line up here. There we go. Weapon damage 100. Okay, not too bad. Then potion toString, potion.toString from health potion. So we have toString being called from this OX200, which is a health potion. So we look in the health potion class for a toString method. We find it right here. So even though we have some overridden toString methods, it's fine. And when we get to this, we have a local variable out, which isn't directly being assigned this method call, so I'm not going to have my return arrow, but I do have this method call, super.toString. So we look at super, which is game item, dot toString. We're looking at a toString method in the game item class, which we find right here. So this is the method that's going to be called for that toString call. So toString, where this is the calling object, is still OX200 when we make super class constructor calls, and when we make super calls like this, the keyword this is still a reference to the same object. And then that's going to return X location, Y location, which I'm not storing in a variable, so it's kind of hidden in the memory diagram, but that's what this is going to return back to this stack frame. So we have out is going to be whatever super.toString returned, which is X colon this dot X location 10.0 space Y colon and then no space after the Y. I'll blindly go by what the code's telling me to do and put no space next to the Y. Even though that's a typo, I'm going to keep it. Y location 0.0. Plus dash health potion, so space dash space health potion. Space bracket this dot increase, so this dot increase 6, and then close bracket, close square bracket. And that's what we're returning. So that gets returned. It gets returned to something inside println. We're not tracing something internal to Java, so we just kind of return and know that that's going to be printed to the screen. So we had a super method call to the superclass's toString method. This was still a reference to the object that was originally calling the method. And then that returned, and we extended the functionality of the superclass's toString method. Oof. Okay, and I think that's the end of these slides. Yeah, we're on the next day. We're making good time today too. We're making good enough time to go back to what I missed. Let me at least briefly talk about what we missed when there was no audio. It looks like it was on the health potion constructor call. So health potion is constructed the same way as weapon. That's just a second example of the same exact thing. But health potion, we call the superclass constructor. Superclass constructor is always, always, always called. So we get game item. This is still a reference to the same object that's being created. And then 2 constructor calls to create that single object. The big thing that we miss is the 2 use method calls. When use is called, which method is actually called? So we have 2 different use methods in our code. We have a use method right here and a use method right here. So we do have a decision to make, or not a decision, but something to figure out, like which one is going to be called. With the previous example, I said here's your progressions and everything, but the progressions didn't really matter so much because for each method call, there's only one definition in the code, so you literally couldn't get it wrong. Like there was no way to call the wrong one because there was only one. But here we have 2 definitions, so we do have to think about this one a little bit. Weapon.use, when we did weapon.use, we're calling from this object right here, which is of type weapon. So we start in the weapon class, look for a use method, we find it here, and this is the method that was called. And then notice that weapon does inherit this use method from game item, but since we found this one first, we never look in the game item class. We never continue with our progressions. Once we find a method matching the signature that we're calling, that's it. That's the one we call. So we call this one. And that's regardless of the override annotation. If this annotation isn't here, we still use this method. The annotation doesn't do anything at runtime. It's only at compile time. That's a compile time check. So this method is called no matter what. Annotation or not. Potion.use is of type health potion, so we go to the health potion class. We do not find a use method, so we continue our progression to the superclass. The superclass has a use method, so that's the method that's called, and the health potion just says item used. So we got damage dealt and then item used. The weapon use method, and then the health potion, which inherited use from game item and just used the default game item method implementation. And we did lose some audio in the slides. Let me just cover my bases and talk about it briefly, though. So the object class, every class in Java either directly or indirectly extends object. Oh no, we did get that. We just didn't get toString. And toString is in the object class. It does this behavior, which we saw before. We printed an object to the screen, and then I said, if you don't want that, you can write a toString method. And we didn't use the keyword, the override annotation, to even further drive the point home that the annotation is optional. It's just a compile time check that helps us write better code and find our mistakes quicker. So last time we didn't use the override annotation because I didn't want to introduce that until we talked about inheritance. But that is what's happening is with or without this annotation, you write a method that returns a string called toString with a capital S. It is going to override the inherited toString behavior, and then that's the behavior that's going to be used when your method is printed to the screen. So now weapon, you call toString. It's going to get the game items toString and call this one. Without that override, you call toString on a weapon. Doesn't find toString, check the superclass. Doesn't find toString, check the superclass, which is implicitly object. Go to the object class, and then you find toString right here and call this method. But if game item overrides toString, now weapon and health potion don't get that default object toString behavior anymore. They'll get the game item behavior, and then we went all the way to what we saw in the memory diagram. Weapon overrode that toString without the annotation, just to make sure we all know the annotation's optional. Overrides this toString, so even though weapon had 3 toString definitions, this is the only one that's ever going to be used from a weapon object. And then health potion overrode, but extended the behavior by making the super call. I'm done with this one. Let's talk about comparators. Oh. Oh. All right, inheritance and comparators. So let's talk about comparators. A comparator is something that's going to compare two values and tell you their relative sorted order. So you give a comparator 2 values, and it'll tell you which one comes first in sorted order. The comparator is very useful. We're going to use comparators to sort by the end of lecture. Let's talk about comparators just themselves before we get there. So comparator comes in 2 different flavors, and we're going to see both of them this semester. The first one I'll talk about, returns an int to tell you something about the relative order of those 2 values. This is the style that Java uses. So whenever you use a Java comparator, like for strings, this comes up. For strings, you want to compare 2 strings while ignoring case. You can call compare to ignore case, and that's going to return some int that follows this structure. It's negative if the first input comes first, positive if the second input comes first, and 0 if the order is tied. We'll talk about this in the next few slides. Let's introduce the Boolean version too. Boolean version, this is the type we're going to write in the course. And this version returns true if the first input comes first and false otherwise. So there's no way to tell directly whether or not you have a tie in your Boolean comparator. There is a way. We actually will see it when we talk about trees and binary search trees. The trick is to reverse the order of the inputs, and then you can figure out if it's a tie or not. But we'll see that later. But these are the 2 styles. And let's talk about ints, because I'm going to introduce them, and then we'll talk about the Boolean style for the rest of our comparator discussions. So the compare to methods, this is what you're going to get if you call compare to or compare to ignore case, or any of the compare to methods that are built into Java. And also Java's built-in sorting methods are expecting a comparator of this flavor. So if you're using any Java's built-in stuff, you do have to know how these comparators work. So these comparators are going to I say take 2 arguments. In the previous slide, I kind of say 2 arguments, but we'll compare 2 values, and these comparators work through, these comparators are being called through an object because they're non-static methods. So these non-static methods are going to take advantage of the keyword this. So when I say the first argument, I'm kind of meaning the keyword this, the calling object. So this will return a negative integer if the calling object's value comes strictly before the argument's value, 0 if they're tied, and a positive value if the argument comes before the calling object. So in this case, I'm comparing 2 strings, and compare to will roughly do alphabetical order, and 1, which is A, I guess I named those variable names pretty confusing. 1 and 2, so A comes before B in fully sorted order. So this is going to return a negative value because A comes before B. The calling object comes before the argument. And then B comes after A, so the argument comes first, so we're going to get a positive value. And then when they're tied, 0. Now, please note, please, these are negative integer, positive integer, and 0. Now, a lot of times the comparators, the way they're written, a lot of times they will return -1, 1, and 0, but that is not part of the spec. That's not guaranteed to happen in every situation. When you are using the return value of a compare method, one of these comparators, you want to make sure you're checking if the output is greater than 0, less than 0, or equal to 0. Those are the checks you have to make. There's a lot of code out there, and I see a lot of code written by students that'll check if compared to equal -1, else if it equals 1, else it must be 0 and it's tied. Do not fall in that trap, because a lot of these methods will return -1 and 1, but not always. So that code is going to absolutely break once one of these compare to methods returns -53. It's still a negative number that still matches the spec, but it's going to break your code. So make sure you're never checking if the output equals 1 or -1. Always greater than 0, less than 0, equal to 0. Those are your checks when you're using these comparators. And just a little bit about sorting strings. I said they'll roughly be compared alphabetically, but they're actually compared based on their ASCII values, which is an integer representation of each character, and all of the capital letters come before all the lowercase letters in ASCII value. So capital Z is going to come before lowercase a, which is usually not what we want. There's no there's no meaning to this. It's just the way that the characters are represented in our code. So we don't want every capitalized word coming before every lowercase word in most cases. So this is why we usually do compare to ignore case. This is what we'll do in task 4. We're going to compare the names of the cast members while ignoring case, because the upper and lower case can be whatever we want it to be. So we're going to compare to while ignoring case, which is a method built into the string class, compared to ignore case. But the default compare to will take case seriously. So if we don't want that to be our behavior, we got to do something about it. That's compared to ignore case. And substrings, if one string is a substring of another, the shorter string comes first, is the other characteristic of this sorting. Other than that, it's alphabetical order. For your homework, if I say sorted alphabetically, I mean use compare to ignore case. For our purposes, you don't have to worry about the details of this. Just make sure you're using one of the Java built-in compare methods whenever you need to compare strings like this. All right, and that's all I want to say about the other style of comparator. The rest of this, we're going to talk about the Boolean style, because I think it's a little simpler to wrap your head around and to write methods that behave like this. So the Boolean version takes 2 parameters. If the first parameter comes before the second, strictly before, return true. And if it comes strictly after or the 2 values are tied, return false. So a bit simpler to write and to think about. So when we're writing a comparator, we're going to write a method that returns a Boolean, which is going to tell us about the relative order of those 2 values. And we're going to write a comparator that's going to sort integers in decreasing value, because it's the simplest thing that's not the default sorting. Usually if you sort, you would expect like integers to be in increasing order. You're going to have the smallest values first. So if we're doing custom sorting, let's do at least something that's a little custom. we're going to sort in decreasing order, which is exactly the greater than operator. The default operator is the less than operator. If you return A less than B, it's going to be true if A is less than B. So that means A comes strictly before B in sorted order, and false otherwise. Greater than is going to give us exactly the other behavior. If A is greater than B, we're returning true. That's when we're returning true, which means A comes strictly before B when it's greater than it, and we're going to get sorting in decreasing order. Now we can make these comparators as complex as we want. We can do all kinds of stuff, but we're going to keep it simple for the lecture. I'll show you one example of a more complicated one. But if we're going to have a method, it's got to be wrapped up in a class. And just a few things to talk about this class, because there's a lot of implications here. It's a combination of stuff we've already talked about, but I just want to make sure we put a spotlight on this and talk about them. So we wrap this up in a class, but this class doesn't have any constructor. How are we going to create an object of type int decreasing? And this is where the default constructor comes in, something I did mention before, but let's make sure we see this again. So every object has every class has a constructor, at least one constructor. We saw ArrayList that had 3 of them. Actually, we only saw 2 of them in this lecture, in the 8 a.m. So every class has a constructor, so you can create objects of every single class. You could say new problem set when you did task 1. It wouldn't be useful, but you can do it because that problem set does have a constructor. If you don't write a constructor, what you get is the default constructor, which is a constructor that takes no parameters and does nothing. It has an empty body, empty parameter list, and is public. This is also why the math class had explicitly a default constructor, is so they could make it private. Because if they don't have any constructor, they get this default constructor, which is public. And then you could say new math, which wouldn't be the worst thing in the world, but there's just never any point to creating a math object. So these 2 classes are completely identical. This is the constructor you get implicitly if you don't have any constructor written. So you do get a default constructor. And we want to use inheritance. I mean, it's inheritance week, ain't it? So let's use inheritance. We're going to create a comparator class that takes a type parameter and has one method that compares 2 values, our comparator method, that's going to compare 2 values of that type. Because we want our comparators to work with any type, so we're going to give it a type parameter. Mostly what we're building up to is sorting. We want our sorting algorithms to be able to work with any type and any comparator of that type. So we're going to have a comparator class, and we're going to extend that class. And when we extend a class that takes a type parameter, we can actually specify that type parameter as we're extending the class. So we're not just extending comparator, we're extending comparator of integer. So we're saying int decreasing is a comparator of integers. And then when we override the compare method, we are overriding a compare method where t is replaced with integer, because t is effectively integer for the int decreasing class. So we're going to write compare to integers and then have our logic here. And here the override annotation really kicks into high gear and really helps us a lot, because if we write this compare method, which I've done this before admittedly, if we write the compare method and have it take 2 ints instead of 2 integers, we're going to think, yeah, we did our job. We overrode that method. Everything worked, and it's going to be auto-boxed. The ints are going to be converted to integers automatically, and everything's fine. Well, everything's not fine. Those 2 methods have 2 different signatures. That means that you do not override anything. If compare takes 2 ints, you did not override this method, and then your comparator's compare method just returns false every time, which is not what you want. This is just some default behavior we gave this method just so the code compiles. Eventually, when we get to polymorphism week, we'll turn this into an interface and make this an abstract method. We're not talking about that today because this day is too stuffed as it is. There's too much content to cover as it is. So we push abstract and an interface over to polymorphism week. We will talk about that.
Not today. So the override annotation really helps us out. If we have the override annotation and we put int instead of integer here, then the annotation, the compiler is going to say, hey, you're not overriding anything. What the hell's going on here? And then you can fix your mistake. I already mentioned that in the previous slide. And I said comparators can get more complex. We're just going to do sorting integers in decreasing order just so we're not too distracted by too many things going on at once. But we can have way too many things going on. So for example, if I want a comparator that compares game items, I can extend comparator of game item, override the compare method to take two game items, and then let's say I want to sort game items by their distance to the origin, to 0, 0. I can write a helper method. Since distance from origin is a full class, I can do everything I can do with any other class. It's not any different that because it extends comparator of game item, I can still do all of my class stuff with it. So I have a helper method. I can write helper methods and then call that helper method from my compare method. And my helper method is going to find the distance from that item's location to the origin by doing some Euclidean geometry here. We could also extend this even further. If we want the distance from origin, if we want to change this to distance from player, we can have distance from player. We can write a distance from player class, give it a constructor that takes a player, stores that player in an instance variable, and then computes the distance from that item to the player's current location, and then compares based on that distance. We can do all kinds of crazy stuff with this. We can compare in any way we can imagine. We can write that code and compare anyway. But for lecture, we're going to stick with int decreasing. But once we have these comparators, how are we going to use these comparators to sort? A comparator only compares two values. What happens if I have a list of 100 items? How am I going to use a comparator to actually do sorting, to actually sort? And for that, well, there are tons of ways to actually do that. Well, we only need to talk about one of them. Let's talk about insertion sort. So just a basic n squared runtime sorting algorithm. If you don't know what n squared means, don't worry about it now. 250 is going to really talk about n squared. Actually, in the next lecture, I'm going to talk about runtime a little bit when we talk about binary search trees. There's no reason to use binary search trees if not for runtime efficiency. So I do got to talk about it to motivate it. But let's talk about insertion sort. What insertion sort does is takes some array or array list, some sequential data structure to be sorted. And what it'll do is for each value in the input, it's going to copy that into the output in sorted order. So we would expect 1 to be copied to the output, then 6 to be copied to the output before 1 because we're sorting in decreasing order, and then 5 to be inserted in between 6 and 1. So that's what we expect to happen. Let's walk through how that's going to work with a comparator. So first, we're going to look at the input 1. Well, that just gets copied over. There's no work to do, nothing to think about. The output array is empty, so we just move it over there. When we get to the first actual decision to make, 6, where does 6 go? Is it going to go before or after 1? What we're going to do is pull out our comparator and check if 6 comes before. Let me think about this. I think ahead to the code we're about to see and try to say this in the same way the code says it. We're going to ask if for each value in the output, we're going to check, does the value in the output list come before the value that we're looking at right now? And ask the comparator one value at a time. Does 1 come before 6? So we're going to make sure 1 is the first argument when we call our comparator. Does 1 come before 6? The answer is going to be no. The comparator is going to return false. So we're going to know that we should put 6 at index 0 in this output array list. Then same thing with 5. We're going to go through everything in the output and ask, does 6 come before 5? The comparator is going to return true. Does 1 come before 5? The comparator is going to return false. Because 6, our comparator is greater than, is 6 greater than 5 true? Is 1 greater than 5 false? And once we see a false, we already know where we're going to insert the value. But in the code, once we get to the code, we're going to see that we're going to count the number of times a value returned true, and that's going to be the index where we're going to insert. So with 5, we got true and false, so we got 1 true. We're going to insert 5 at index 1. So our comparator can only compare 2 values at a time, but we can use that to do a full sorting algorithm. So we can write the insertion sort algorithm using a comparator and just asking, what about these 2 values? What about these 2 values? What about these 2 values? Which one comes first? And the comparator is going to be called many times, depending on how big the array list is that we're sorting. We're going to call it many times to be able to get our fully sorted order. But we only need to define how to compare 2 values to get our algorithm to work the way we want it to. And here's the code. I'm just going to throw the code at you, and we're going to talk about it for quite a while. Here's the code that's going to sort. I'm going to have a sorter class that's going to implement insertion sort as a method called sort. And it's going to take a comparator. And then we're going to use it to sort that list that we saw in the previous slides. So first, sorter is going to take a type parameter t, and it's going to take in its constructor and store in an instance variable a comparator of t. So we're going to create a sorter that sorts a specific type, and we need a comparator of that type so we know how to compare 2 values once we have 2 values of that type that we're trying to sort. Then the sorting method, we're going to create a new array list that we're going to return. We're going to create that output array list. And this is a general thing that we have to be concerned about with objects. Whenever we write a method that takes a reference to an object as a parameter, we have to be careful about going over to the heap and making any changes to that object, because those changes can be seen from outside of that method call. So if main calls sort, and then that input, we trusted that method call with our array list, if it makes changes to that array list, we're going to see those changes here. List will be modified if that was changed at all, which might break the code that called your method. So whenever you get a parameter that's of a reference type, you want to be very careful about what you do with it. In general, don't make any changes on the heap to that object unless that's the goal of the method. Like if you're writing an add method for array list, the whole purpose of that method is to add an element to that array list. You're going to want to go to the heap and make that change that you're supposed to do. Same with like setters. The whole point of calling that method is to go to the heap and make a change to that object's instance variable. So you want to do it then. If the method isn't intended to make any changes, don't make any changes. Don't make any changes to that object, because you might break the whole project, and other code that calls your code, things are going to break. So be very careful with that. It's general advice, but it comes up here as well. So to avoid it here, we're going to create a brand new array list. That's our output array list, and that's the one we're returning, and we will leave the input array list completely intact. Some sorting methods are called, and with the behavior of wanting to sort the input, go to the heap and make changes to it and sort it. But for our purposes, we're not doing that. We're leaving the input intact. We're not changing it at all. And we're going to return a new array list that is the output array list. Then we're going to do our actual sorting. So we're going to go for each value in the input array list. We're going to initialize location to 1, our accumulator variable. And we're going to go through the output array list and count the number of times comparator returns true when we check the value from the output list to the input. So we're asking the output list, how many values in the output come before the value that we're inserting. If we count that number will be exactly the index where we insert. So for example, if that number is 0, if there are no values in the output list that should come before the value we're inserting, then we should be inserting at index 0, because that value comes before every value in the array list. Or possibly there's ties, we could have tie situations, but we're going to break ties in this case by the value we're inserting is going to come before any other values that were already inserted that were tied. Technical, it doesn't really matter for the context of what we're learning right now, but that's how this code would behave. But we're going to count the number of values that come before it and then insert in that index. And we're going to use an overloaded add method. We've only used the add method that takes one parameter so far, but we can actually call this one that takes two. Add here is going to take an index, the index where to add, and then the value to add. So we're going to add value to insert at index location. And we have one really big potential issue here. We have sorter, which takes a comparator of t in the constructor as a constructor parameter, and then when we call the constructor, we give it as an argument an object of type int decreasing. And int decreasing does not equal comparator of t. And I've been saying since day one, Java is strongly typed. If you have a variable of a type, it can only store values of a type. So what are we doing here? Like, what's going on? Why do I have comparator equals int decreasing? Is this even allowed? Does this code even compile? Or is this just broken code? And, well, it is allowed. This is actually allowed. This compiles, it runs, everything's great with this code. And the reason it's allowed is for a little thing called polymorphism, which we have an entire lecture on later in the semester in 2 weeks. We have an entire lecture on polymorphism to talk about why this is allowed. But the short of it, the TLDR of this is because int decreasing extends comparator, it is a comparator in the sense of variables in strong typing. It is a comparator because it extends comparator, so it can be stored in variables of type comparator. And in a nutshell, that is polymorphism. If a variable, if an object extends a type, it can be stored in variables of that type. So since int decreasing extends comparator, it can be stored in this variable of type comparator. In fact, this is the type here is integer, so this is comparator of integer, and int decreasing extends comparator of integer. So this is a valid assignment. Everything's fine here. Much more to talk about with that in 2 weeks when we have the polymorphism lecture. But for now, just suffice to say, this is allowed. This is allowed, and it's a very cool topic that we'll have some fun stuff to talk about when we get there. I think it's just a memory diagram. Let me see if I have any cleanup slides. Nope. Just a memory diagram. Let's do it. Trash can, all that. Hide toolbar, full screen. And this one fits much better. Okay, let's do it. Everything starts with main. Half an hour to trace this thing. We got this. Sorter is going to equal a new insertion sort, but we do have to resolve what's inside the parentheses first. So we got a lot going on this first line. We have to resolve what's inside the parentheses first. This is going to be a constructor call. It doesn't return to any variables, but we still have to resolve this before we can get sorter doing its thing. So int decreasing constructor. Int decreasing constructor this. We're going to create a new object of type int decreasing. And we got a lot of weird stuff going on with this int decreasing thing. A lot of stuff that I won't throw at you on a quiz because I don't know if it's super fair. But a lot that I want to at least mention in lecture. Int decreasing, we're going to call its constructor. It doesn't have an explicit constructor, which means it gets the default constructor. Default constructor takes no parameters, so we just have this, and that's it. And it doesn't do anything either. And I say it doesn't do anything. It has an empty body, but we're about to see something pretty soon here. Before that, we need to get our instance variables on the heap. And I look at int decreasing, I don't see any instance variables. I go to the superclass, I don't see any instance variables. So this object actually isn't going to have any instance variables, which is usually a good indication that this could be static method. Compare could be static, but I want to create objects so we can talk about inheritance and stuff and have comparators. Even though we don't have any instance variables, it's still kind of the Java way. Sometimes we just want classes and objects. Specifically objects. We have to have classes, but specifically objects. So we have no variables. So we have the default constructor, which is being called, but remember I made a big deal that the superclass constructor is always, always, always called. That still applies even though we have the default constructor. So I keep saying it doesn't do anything if you have the default constructor. It's not strictly true. There is still that implicit superclass constructor call. There wouldn't be any code in the body, but even if there's no code, the superclass constructor is implicitly called. So we have an implicit call to the superclass constructor, comparator. And comparator also doesn't have any explicit constructor, so it also has the default constructor, which doesn't do anything. Technically, it does call the object classes constructor, but that's internal to Java, and we don't trace that since it's internal to Java. So this returns, it doesn't really do anything. This returns, doesn't really do anything. And then this whole thing resolves, after all that, this resolves to OX100, that reference. So we have a bit going on in our memory diagram, in memory, that doesn't have a whole lot of effect on the program. But these two constructors are still called. They do still absolutely happen. Then we can finally put insertion sort constructor on the stack. With this, it returns to sorter. We see the keyword new, so we have a new insertion sort. Map the constructor. This, we got OX200. We have one parameter, which is comparator, which is OX100, what int decreasing resolved to. It resolved to the object, a reference to the object that was created, OX100. So we have comparator, and then this dot comparator. Oh, I didn't do the instance variables. Comparator, one instance variable. No superclass, so no other variables. And then comparator equals comparator. This dot comparator equals comparator, OX100. And then insertion sort constructor returns to the sorter variable in the main stack frame. Then we are creating an array list. So we have list. The array list constructor is internal to Java, so we don't bother tracing it. Same with the asList static method call. We're not tracing any of this because it's all internal to Java. We just have to know that we got a new array list out of this method call. We got a new array list. There's no constructor to map because we didn't map it to anything. And the indices 0, 1, 2 get the values 1, 6, 5. We got OX300 as the reference for that object. So that's what we put in list. Then we're ready for our sort call. This is the big one that we're tracing today. Sorter.sort. Sorter.sort. Sort is called from OX200. Takes an argument of list. I didn't look at the parameter yet, but I know the argument is going to be OX300. Sort from object of type insertion. Sort is called input. Then we're creating a new array list output. has nothing in it right now. We got OX400. Then we hit our first loop. So we have our code block, because value to insert is going to be created inside of the for loop. And it's going to iterate over input. So input is this array list right here. The first value is 1, so value to insert is going to be 1. We're going to have int location equals 0. We're going to hit another loop that's going to iterate over output. Since output is an empty array list, this loop actually isn't going to be executed at all. We're going to completely skip over it since output is empty and it's a for each loop, nothing to do, and we get right to output.add. So output.add, from this array list, we're adding at index 0, location is 0. So at index 0, we're inserting value to insert, which is 1. We hit the end of that loop, so value to insert is going to advance to the next value in this array list, 6. Location is 0. We're technically redeclaring a new variable, but we're not going to mess with the intricacies of that. I'm going to pretend that this is a reassignment and assign it 0. Yes, I'm just crossing out 0 and putting 0, but that's fine. And then we hit the inner loop again. This loop does have something in it. The output array list does have something in it, so this loop does execute this time, and we have a code block inside of a code block, which is absolutely allowed. We can do that. We can never have a stack frame inside a stack frame. We can have a code block inside a code block. That's perfectly allowed. And we have value to compare, which is iterating over the output array list, which just has the value 1. So we're only going to do one round through this loop. So value to compare, and we're going to call comparator.compare. So comparator, oh no, I don't have my this. That actually tripped me up too. This dot comparator dot compare. So we're calling compare from this object right here. So we have compare, where this is OX100. That's of type int decreasing. So I look at int decreasing for the compare method, not comparator. I'm not just getting the return false. Since it's of type int decreasing, I look at this method here that has parameters a and b. A, that's a 1. A, B. And gets value to compare, which is 1, and value to insert, which is 6. And it's going to return A greater than B. A greater than B, that's false. So this whole thing returns false, which means we do not execute the if block. And we go right to the end of our loop. Our loop was iterating over output. Value to compare of output, value to compare is 1. So we go to the next value, which that's the end of the array list. So that's the end of this loop, and we add to our array list again. So output dot add at location. Location is 0. So at index 0, we're adding value to insert, which is 6. So we're going to update at value 0. That's now storing the value 6. And when we insert at a specific location, anything at that location and after is going to be pushed down the array list. So we're not strictly setting the value at this location. We're adding a value at that location and preserving everything that was already in the array list and moving them down, down in the array list, down to the next indice. So 1 got pushed down to index 1. Okay, then we hit the end of our loop again. So value to insert advances to the next value, 5. location, reassign 0 again. And then we hit our inner loop. We're going to iterate over the output array list. So first 6. Oh, sorry, this code block ended. And then we're going to create another code block, again for the same loop, but it is a different code block. We're hitting it a second time. Value to compare. Because we hit the end of this loop, we had to remove its code block from memory. So this code block is gone. We create another code block for the next time we hit this loop. This is a new code block for this second time, and we have a new copy of value to compare. Value to compare is iterating over output, which starts at 6. And we're going to call our comparator again. This dot comparator dot compare. From this object, we're calling the comparator, or the compare method. So compare this OX100. We have A and B, which are value to compare. Value to compare is 6. Value to insert is 5. Since OX100 is of type int decreasing, we get this compare method here in the int decreasing class, A greater than B. A greater than B is true. So this is going to return true, which means we do execute the if block and increment location by 1. So we found one value that comes before the value we're inserting. We hit the end of this loop. This time output has more than one thing. We're going to advance to 1. So value to compare gets the value 1. And we're going to do it again. This dot comparator dot compare. Compare this OX100 A, B. Value to compare is 1. Value to insert is 5. 1 greater than 5, that's false. So we do not increment location again. With the end of our loop, our value to compare is 1. That's the end of our array list. So we're crossing out this block. And output.add location value to insert. So output.add. So we're adding to this this array list location at index 1. So we're replacing this value with value to insert, which is 5. And since we had 1 there, we're going to push 1 all the way down to index 2. We reached the end of our loop again. We're iterating over input with value to insert. We did 165, 165. Looks like we're done with that. So we're done with the, oops. So we're done with this code block for the outer loop. And then we're going to return output. So output, oops, missed one thing here. I didn't put my variable on the stack here with my return arrow. So output, return output, OX400. So this returns OX400 right here. And one last thing, we print output to the screen. So print this to the screen. 6, 5, 1. And the main stack frame ends and the program's over. So quite a bit going on. In this loop, with the inner loop and method calls inside of a loop, this is a little more complex than anything I would give you on the quiz. So if you understand everything with this memory diagram, you're going to be just fine. I mean, aside from, well, I guess we did inheritance here. If you understand everything here, you're going to be fine on the OOP quiz. But if you're a little fuzzy on exactly how the intricacies of this triply nested code block thing happen, if you're a little fuzzy on that, you still might be fine for the midterm. I would still study. You should be able to at least follow this trace. But if you couldn't look at this code and produce this trace exactly right, I wouldn't be too worried. You still want to study. You still want to make sure you can do that. But this will be a little more complex than anything I give you on a quiz. And somehow we finished 15 minutes early today. Oh, man. I guess I'll take any questions. If not, I might just end the stream. I didn't miss anything, right? We covered... I even went back and recovered the stuff when the mic was out. Talked about the object class. Yeah, we got everything. That's inheritance. I guess I can talk about the homework a little. Okay, so is there anything specific I need to highlight here? I don't think there is. Let's pretty much go through the thing. Bayesian average trips students up. I think I got enough explanation to understand what Bayesian average is. Make sure you get your edge cases with Bayesian average. That's one of the common office hour questions. When ratings are invalid, when there are no valid ratings, and when you call Bayesian average rating with 0 extra ratings. I think I have them all covered in bullet points here, but those tend to be the most common questions, is all the edge cases with Bayesian average rating. When it comes to your testing, like, just make sure you test all the edge cases. There's a lot of them with Bayesian average rating. Just make sure you're testing them all. A song or movie that has no valid ratings but does have ratings, but all the ratings are -1, is a good edge case. And whenever you're calling Bayesian average with 0 extra ratings, so what happens when there's no valid ratings and you call Bayesian average with 0 ratings? It's a case where it'd be easy to have your code blow up in that situation, have a divide by 0 error. So it's a situation we want to have a test case for sure. And comparators, you write a few comparators. Don't overthink these comparators. You have compared to ignores case. You don't have to go through all the different combinations and understand how the sorting is happening. Call compared to ignores case. This is a test in comparators, making sure you understand that this is going to return a positive number, a negative number, or 0, and what to do in each of those cases. That's what you're expected to do here. This should be like 1 or 2 lines of code. Actually, 1 line. There's no reason to have 2 lines even. But don't overthink that one. I've seen some students overthink this one and have a lot of complexity there. You don't need complexity. Comparing array lists, ignore case. This is a situation where you can't just use assert equals. This is written in a way that's forcing you to go through each value in the array list. First, compare their sizes. Whenever you have 2 data structures that you're comparing in a test case, compare their size first. If they're not the same size, you're done. They're not the same. Just, assert that they're the same size. If that fails, then yeah, they're not the same. If they're the same size, then you want to go through the indices and compare pairwise the values at index 0, the values at index 1, the values at index 2, and call this compare to ignore case. Or there's also equals ignore case when it comes to strings. So you can use those. Yeah, that's really all the hints and common issues that I see. I don't see any questions in chat, so I'm just ending this one early. That's inheritance, baby. I'll see you next week for trees. Take care. Good luck on the programming tests. Have a good one.